All right, welcome to 1.4, which is talking about something called the inverse of a relation. So we're going to be using some algebra today to determine the equation of inverse relations and graphing those things. So this isn't totally connected to what we've been doing so far. The connection is that we are graphing relationships between different functions, but we will not be using things like the transformations in this section. So before we start, we need to make sure that everybody's good on their basic algebra skills. So these 4 questions here, I would like you to try. So if you can please pause the video, try these questions, and then continue so that you can see if your answers are correct. That would be great. So your idea is to isolate y in these 4 questions, please. All right, now this means you have unpaused your video and you can take a look at your answers here. So just a few reminders. One, when you're solving for y, if you do something like in number 1 where you have to divide by 5, you must divide the entire left-hand side by 5. A lot of people will say this is 1 over 5x plus 3. The over 5 is underneath the entire x plus 3. The other reminder for number 3 and 4, when you have to square root because you have that y is squared, a reminder that that would be plus or minus root of the x stuff. You need that plus or minus in front because if I have something like 25, if I square root that, I don't know if the answer is 5 or negative 5, right? 5 squared is 25, negative 5 squared is also 25. So if I square root 25, my answer is plus or minus 5. So here, if I square root, my answer is plus or minus the root of the x stuff. So before we move on to actually graphing and solving some inverses today, definition of an inverse relation, okay? So for example, number 1, y equals 5x minus 3. If that is our original function, our inverse is y equals x plus 3 over 5. So this guy, if the first one had y equals 5x minus 3 instead of the x and the y where they are, these are inverse relations. Okay. So in an inverse, the operations are reversed and are in reverse order. So in our examples here in the box, the first one we are multiplying by 5 and subtracting 3. The second one we are adding 3 and dividing by 5, and we're doing it in the reverse order. So operations are reversed. And are in reverse order. Okay. To determine an inverse, the simplest way we're going to interchange or swap the x and the y and then resolve for y. Okay. Once we get going, I find that people find it a little bit easier once they've seen a couple examples. Once you get going, it really is quite straightforward here. Okay. So for example, if this is our function, y equals 3x minus 6, we're going to graph it and graph its inverse. So before we graph it, we need to find the inverse. Okay. So to find the inverse, we're going to swap the x and the y. Okay. And then we're going to solve for y. So I end up with x plus 6 equals 3y, or x plus 6 all over 3 equals y. We want to be able to graph this, so I'm going to rewrite this as 1/3 x plus 6 over 3, or 1/3 x plus 2 equals y. Okay, so this is my inverse here. Okay, so we're going to graph these two functions. So our first function is y equals 3x minus 6. So just a reminder, this is your y-intercept at the end, and this is your slope front. If you can't graph straight lines, this course is going to be quite difficult for you. So I would make sure that you are brushed up on graphing of your straight lines and your parabolas. And if you are given a function, how do you graph from that function? That should be something that you are comfortable with for this course. There's a lot of graphing. Okay. So here I've got, let's do it in black, the original one here. So my y-intercept is -6. And then my slope is 3. Rise of 3, run of 1. Rise of 3, run of 1. Rise of 3, run of 1. I'll include one more down here. Okay, and then we're going to connect those points. And hopefully a semi-straight line here. Don't have a ruler, so might not be perfect. Right? And then we have to graph our inverse as well. So this one would have a y-intercept of 2 and a slope of 1/3. So up 1/3, up 1/3. Go the other way a little bit as well. If I graph those too fast for you, feel free to pause or scroll back if you need. So what do we notice about the two graphs? So hopefully we notice a couple things. Okay. We can see that they intersect at this point here. Okay. And the reason that they intersect there is because x and y are equal. Hopefully we notice that the slopes are reciprocals. So the slope of this one is 1/3. The slope of this one is 3. Hopefully we notice that our x-intercepts and y-intercepts are interchanged with each other. So our x-intercept on our inverse graph is at -6 and our y-intercept is at 2. On our original graph, our x-intercept is at 2 and our y-intercept is at -6. So our x-intercepts and y-intercepts switched with each other. And that is not just for those points. Okay. All of our points on our original graph on the black line, the coordinates of those points, if I take the x and the y values and switch them, those become the coordinates on our inverse. So for example, if I take a look at this point right here, this point is at 1, -3. That means on our inverse function, there should be a point at -3, 1, which there is right here. Okay. So the points are interchanged. Okay. Or the x and y values of points are all flipped for the inverse. What this means is if you have not been given an actual function, an equation you can use and resolve for y for, if we're just given a graph and asked, please graph the inverse, we can. All we have to do is flip all the points, and we're going to do that in an example on the next page. So take a look at this. I don't have a function. I have no y equals where I can swap my x and y and resolve for y. But I know that the points of f of x and the points on an inverse, the x and y coordinates swap with each other. So this point here, for example, this point here is at -4 comma -2. That means on my new graph, the point is going to be at -2 comma -4. So I'm actually going to move where my label is because I'm going to run out of space otherwise. So this is -4, -2 right now. My new coordinate is going to be at -2, -4. Right here. This point up here is at -1 comma 4. That means my new point is going to be at 4 comma -1. Connect your dots. Okay. The next point here, we have this point is at, let's see, what is that? 3, 2. That means my new point is going to be at 2, 3. And the last one here is at 6, 3. That means the new point is at 3, 6. Okay. Again, I would move left to right, connect as you go. Okay. The other thing that hopefully we're starting to notice is that it kind of looks like these are reflections of each other. If I look at this one and I look at this one, they kind of look like a reflection across a diagonal line, which they are. If I draw a diagonal line through y equals x, these are all reflections across the line y equals x. Next, we're going to find domain and range of both graphs. So f of x is the original one. Remember, your domain is what x values are allowed. How far does this span left to right? So on my original graph, my domain, my smallest x is -4. My biggest x is 6. On my range, my smallest y is -2. My biggest y is 4. On your inverse, my smallest x is -2. My biggest x is this guy here, which is at 4. For my range, my smallest y is -4, and my biggest y is 6. So the next question is, how are the domain and range for both graphs related to one another? Hopefully you can notice here that the domain on my original function became the range on my inverse. And that should make sense because my inverse function, all my points, my x and y's are swapped. So on my original graph, all my x's are my domain. On my inverse, those x's have now become y's, which would be my range. The same is true for the opposite. My range of my original function is now my domain of my inverse. Okay. So the domain of f of x becomes the range of the inverse. Okay. The range of f of x becomes the domain of the inverse. Okay. All right, let's move on to the next one, last one. So we're going to graph 2x squared minus 3 and its inverse. That's the first thing we're going to do. The second thing we're going to do is it's asking us to restrict the domain so that the inverse is also a function denoted by f with this little -1 of x. So anytime you see this notation, this just means inverse function. So not every inverse is a function. A reminder about something to be a function from grade 10 means it must pass the vertical line test. So what that means is if I draw a vertical line anywhere along the graph, it should pass through the graph at most one time. Every input has at most one output. Every x value can only have one matching y value, okay? So something like this is not a function because if I draw a vertical line, this x value has two y values, okay? All right, so let's start at the beginning. We are being asked to graph this function. This is a parabola with a vertex of 0, -3 and an a value of 2. Okay. So our vertex is at 0, -3. Our a value is 2. That means that our normal pattern is all doubled. So when I go over 1, I'm not going to go up 1. I'm going to go over 1 and then up 2. And then over 1, and instead of going up 3, I'm going to go up 6. Okay. Could go again, but I'm going to run out of space, so I'll stop there. So this is my y equals 2x squared minus 3. So for our inverse, we have two options. We can go based on the function, the equation we've been given. We can swap x and y and re-isolate for y, or we can use the graph and switch all the x and y values. Okay? Either one is fine. I'm going to do the graph way first, and then I'll also show you how we can do the equation. Okay. So my first point here I'm going to do, oh, my word is just a little stall there. My first point here is my vertex, which is 0, -3. My new point would be -3, 0, which would be right here. I have a point at 1, -1. That means my new point is going to be at -1, 1. There. That one would correspond with this. This point here is at -1, -1, so it's going to stay in the same spot. Okay, I'm getting too many blue things here. Let me just fix this up a little. Okay, so we've done the vertex. We have this point that doesn't move here because the x and the y coordinate are the same. We've moved our other first point from the vertex. We've moved that 1, -1 point. So now we have these upper 2 points that we need to move as well. Okay. So the one on the right is 2, 5. That means our new point is going to be 5, 2. Our one on the left is -2, 5. That means we're going to be at 5, -2. Okay. So this is our inverse. This would not be a function right now, because if I draw a vertical line anywhere through this graph, it's going to cross twice. All right. So the question is asking us to restrict the domain so that the inverse is also a function. So in order for this inverse to be a function, we would have to have either only the top part or only the bottom part. Okay. So if we have only the top part or only the bottom part, that would mean on the original function, we either have only the left or only the right. The domain of the left portion only, here, my domain of this, okay, so to be a function, or so for, let's be more specific here. For the inverse to be a function, the original graph would have had to be only the left portion or only the right portion. Okay. The domain of this original function is all real numbers, right? Domain of a parabola, I'm allowed to go left and right forever. The problem here is we either want to go only to the left or only to the right. So only left would have been only these values here, which would have been if x was less than or equal to 0. If we only had the right portion of our parabola, that means our x values would have been only these ones here. Which would be if x was greater than or equal to 0. So for the inverse to be a function, we could only have the top portion of the blue or the bottom portion of the blue, which would mean we could only have the left portion of the black or the right portion of the black. If we had only the left portion, x would have had to be less than or equal to 0 only. If we had the right portion, x would have had to be greater than or equal to 0 only. That would be the two different ways we could restrict the domain of the original graph so that the inverse becomes a function. Okay. Now the second part of the question has been answered. And the only thing is that I think there's going to be some of you who don't like working off the graph and would rather have an equation. So if you had wanted to find the equation of the inverse, we would have had to swap x and y and then resolve for y. So I'd get x plus 3 equals 2y squared, or x plus 3 over 2 equals y squared, or plus or minus root x plus 3 over 2 equals y. Okay. So here, the plus or minus, if you think about this, what does a root graph look like? It looks like this. Okay. So actually here, the plus part is this top root. The minus part is the bottom root. So the graph does actually match our equation here. The top is like a root graph that has moved to the left by 3 and been compressed or expanded by a factor of 2 horizontally. The bottom part has also been reflected. Okay, so our equation does match our graph here. Let's get rid of all this because it's quite messy. Okay, if you wanted to go based on an equation, you could. Okay. So just a summary of all of this stuff that we have covered for inverses. Okay, so an inverse is a reflection across the line y equals x. Okay. For graphically, all x and y coordinates swap. Algebraically, to find an inverse, we swap x and y. And resolve for y. Okay. And the domains and range of f of x become the range and domain of the inverse. Okay. That is all for 1.4. Again, please try some practice questions. And that's it.